Welcome everyone. It's an honor for me to be here. Sorry, a moment. So during this story, I want to mention that I think we who learned with Tamás Roska cannot be thankful and graceful enough to had this experience to learn from him, and most importantly from me, from the mountain of gifts that we received from here. The most important, and I think at the peak of the mountain there are two things. So it's rather at the summit of the mountain. Two things, and one is I think his worldview and his really reliable moral compass that we received from him, and this encapsulated science, faith, and art together. And I think the other thing is, which is related to this and related to one of the citations from him, from Ildikó Csurgai's talk, which goes back to the miracle of understanding, that he never just shared his vision or revealed his truth, but most of the time he motivated us with questions, and it was important, I think, for us to make us understand his worldview. And for me, that's really important, that I think this is the most important. But I also think other people can and have talked about this significantly better than I could ever do. So I will speak more about technical parts and technical details, which would involve modern machine learning. So I think I don't have to speak much about the current artificial intelligence and the state of artificial intelligence, and many decades were presented in the past decade, and this process started in 2010 and 2012. So luckily he was also able to see the first steps in his life, what he paved. And there are many advancements, from the proof of concept of self-driving cars, face recognition, AlphaGo, or ChatGPT, and I think we are all familiar with these breakthroughs. But also there are some problems with this, because I think here solving these problems are really important, and everybody works on that. And we don't really do this with enough efficiency. These models contains a vast amount of parameters. Some of them contains like 800 billion parameters, and or 800 billion neurons. And with this, we can undeniably solve amazing problems. But just, I think last week it was introduced how scientists mapped like the whole brain of a fruit fly, which contains around just 130,000 neurons. And so these animals, of course, they cannot cite Shakespeare or write and so many things, but compared to like this amount of computational power, are extremely complex. So I think that there has to be something more behind this than just using simple digital elements and neurons and transistors. And so I think in one of the central element of his research was cellular neural networks, which were showed, and here it's presented by a differential equation. And the details are not really important, but I think it's really important that this is a continuous network, an analog neural network, which is significantly more efficient than the current implementations of digital neural networks. So if we think about ChatGPT, just for ChatGPT, answering one question is about like 5 watt-hours, consumes 5 watt-hours of power. And even in our lab, we have machines which consumes and 2 watts of energy, like the whole chip, which are in complexity, I think, still more energy efficient than some of the current implementations. And although analog neural networks are noisy and not that efficient in many parts, but it can be shown that they can work better. And in this concept, we changed like 2 minor things, but I just want to show that, and I think this could be important later in the talk, that the standard cellular nonlinearity looks like this, which thresholded values, if they were below a certain level, they say that there's no signal, but they also have an upper bound when they say that they cannot have like an arbitrarily strong activation. And here we made just some minor modifications in the equations to assume that all parts of this equation provides gradients because the derivative of this and this is 0. And with this we have a toolbox which unfortunately we don't have analog implementations of Professor Roska's invention and the cellular neural networks, but we can simulate it with digital hardware. So we try to merge this with current frameworks which are used in artificial intelligence, in TensorFlow and PyTorch, and I just want to show some results regarding for this. And one of the interesting things that in certain aspects of problems, for example, this is segmentation, from self-driving cars, if you look like a scene there, and if you try to solve this with a really simple problem, there are significantly better solutions in digital, but this is just to show if the complexity is the same. A 4-layer neural network gives a really noisy solution here. But if you try to solve this with a 4-layer cellular network, so here the red parts would be obstacles where the car cannot go, the green part would be the free road, and the yellow parts would be moving obstacles. You can see that the same hardware complexity when the solution is analog, and of course in this setup everything is ideal, not noisy and things like that, but this architecture of 4-layer cellular neural network can provide a significantly better and more accurate solution, and you can see this in certain set of numbers. Another thing why I think like this nonlinear trained vision is really important in artificial intelligence, because one of the I think most crucial problems with current artificial intelligence is that for certain inputs it works really well, but if we go further from the training set, sometimes it gives unpredictable results and hallucinate things, but hallucinate them with really high confidence. It will never give you answers that I don't know this answer, but even if it doesn't know, it will give certain but wrong answers. And one of the reasons behind this is that in current artificial intelligence, and this provides the highest possible accuracy, is something called as a nonlinear function, the rectified linear unit and its variants, where this is a lower bounded function, where so below a level there's no signal in this output function, but it allows, like this part is completely linear, it allows arbitrarily large activations. So what happens in a neural network is that we can find certain inputs where the result from all these millions or billions of neurons will be dominated just by one or just by 2 or 3 of them, which gives really certain answers, and all the others are silent. In the neural networks which Tamás envisioned, this cannot happen, because he also used an upper bound for the activation of the neurons. And this can be used, like, to show these results, the most important aspects, I think, are adversarial attacks. So, for example, image recognition software, which works perfectly and recognizes this image as a banana normally. But if you present, like, a special sticker, and the sticker contains some strong features of a toaster, then it will recognize the image as a toaster, because these few neurons will be just more certain than the neurons which are seeing the banana. And this can be done with traffic signs, and like, for example, if we use this special kind of attack and the stickers, then the algorithm will think that this is not a stop sign but a speed limit sign. So this can be critical, and if we change this nonlinearity just by that, here you can see some qualitative examples, but by the results you can see that if we use this bounded nonlinearity, the number of possible successful attacks, which were, for example, 76% in case of the normal rectified linear unit, goes down to 0.5%. And in another case, from 80, it goes down to 6%. So this is something could be still leveraged from his insight and not used in machine learning. Another important aspect what I want to speak about, and is extremely popular nowadays, are generative models. So generative models are something where we don't want to like seemingly solve a problem for the first glimpse, but we have some training data of like images of horses, and we will just simply train a model to generate images of horses, and by this to understand how horses looks like. And this can be used in practice, and there are some nice examples for this from image generation. I just asked DALL-E to generate an image from Budapest, and I think although there are some strange looking churches at the background, the image like painted just by memory of the neural network, whatever this means, is I think still amazingly good. And I could also ask him to create buildings where the walls look like printed circuit boards, and it can solve this problem fairly well. And there are other examples as well. It can basically draw anything that we ask from that, from a cartoon. Here you can see the descriptions, or just wonderful Cycladic houses with blue accent and like in a Greek island setting. So there are amazing results here. Of course, there are failure cases because they don't have a word model behind that. These are two of my favorites. If we ask it like how salmon looks like swimming in a river, these are slices of salmons in the river, which is okay, partially correct. And the other is a seal of approval, which should be a stamp normally, but you can see here that it draws a nice animal. But this can also be used in practice. Because if we just use this text continuation or image continuation, we can ask how, like this famous image, the girl with a pearl painting, would look like around it. And of course, it generates some plausible results. But we can also, just in text continuation, ask a question, and these large language models will provide correct answers for many of these examples. And what I just want to mention in the few last minutes, that behind these algorithms are a diffusion process. And this diffusion process is a discrete diffusion, where in training we have a perfect image and distort it by noise step by step. And we will try to invert this process, where from noise we create an image. And this is discrete in its nature, but we mimic diffusion with this. And of course, this diffusion process is something that fits ideally of the cellular neural network, which were invented by Leon Chu and Professor Roska. And if we try to do this, here are some comparative results. Instead of a digital implementation of a regular convolutional neural networks, and these are some real handwritten numbers, if we use an analog implementation of nonlinear diffusion, which is inherently what is behind the process and not just trying to mimic it with discrete steps, we get significantly better results. So with this, I just wanted to show a few aspects, I think, which can still leverage from the inheritance and the guidance of Professor Roska with the current state of deep neural networks. And some of these are the energy efficient analog implementations. The other is the bounded nonlinearities in neural network, which provide like more robust implementations. And the third would be continuous time neural networks in stable diffusion and generative models. And of course, I also have to mention that some of the aspects are still not utilized or underutilized, such as the effect of feedback, which we believe is really important, and I also believe was important in his network, and none of the current implementations have those. And I think I'm really happy that he was able to, in his life, was able to see the first steps of this renaissance of neural networks. And I know that from another point of view, he still sees and I think is happy that neural networks are more central in research and applications. But on the other side, I also can't help just to think about how much we could have reached if we would still have his guidance once on the technological level, and also I think which becomes more and more important in the application of intelligence on the moral level. So thank you for listening to my talk. Thank you.